Okay, so the first one is 5 sine x plus 2 equals sine x.
Okay.
Okay.
Well, what can I do here?
Could you subtract the sine x from the right side?
Okay. So that gives me 4 sine x. And then if I put the 2 on the other side, I get that.
So
Now what?
x. Divide by 4, right?
Huh?
And then you could reduce that.
Sine x equals minus 1/2. I presume when they gave you this problem, they gave you the domain. Probably said
Uh,
greater than or equal to 0, less than or equal to 2 pi.
no, it just says solve each equation for all values of x.
Okay, that's different. In other words, they want not just the unit circle answers, but all answers. In other words, what are all of the answers of x that this is true? Well,
Isn't it for like, never mind, sorry.
no, that's okay. What's one value of x where this is true?
One value of x, where this is true, is 5 pi over 4.
No, that would be the equivalent of pi over 4. First of all, what's the first quadrant angle where the sine of x
Oh,
is equal to positive 1/2?
pi over 6.
Right, or 30 degrees.
Yeah.
Okay. What's another quadrant? In other words, in the second quadrant, sine is also positive. Hold on.
Mhm.
Let's go back here a second. So 30 degrees or 150 degrees would satisfy sine x equals 1/2.
Mm-hmm.
Well, we need to satisfy sine x equals negative 1/2. What two quadrants in the unit circle is that true?
The third and fourth quadrant.
Okay, what's the angle in the third quadrant that's the equivalent of 30 degrees?
7 pi over 6.
Yeah, I'm glad to see you thinking in terms of radians. That's also 210 degrees. And how about the fourth quadrant?
11 pi over 6.
Which is 330. So, in the unit circle, these would be the two answers.
Okay.
Okay? But since they want all answers, then the first one is 7 pi over 6. And any multiples of that, right?
Uh,
So in 7 pi over 6, let me think for a moment. Hold on. Let's go back for a second. And list the two angles in the unit circle. Okay? In other words, if our domain was unit circle only, these would be our only two answers.
yeah.
Question is they want all answers. In other words, they want 7 pi over 6 plus 2 pi. That's another answer. In fact,
Mm.
multiples of 2 pi are other answers. Where n, do you use n or k?
And our thing came out to be 2n pi.
Okay, or n 2 pi, doesn't matter.
Yeah.
It's a little more
Mm.
understandable actually when you think of it as n 2 pi because we're looking for multiples of 2 pi above 7 pi over 6 or multiples of 2 pi over 11 pi over 6. In other words, if n was 0, then it would just be 7 pi over 6. If n was 1, then that would be 19 pi over 6. So that's also an answer. If n were 2, that would be 31. I'm doing my math. Yeah, no, that's correct. 31 pi over 6. So that's a correct answer. That's a correct answer. And then our second answer, if n were 1, then that would be 23 pi over 6. You see where I'm getting these numbers? I'm adding 12 pi over 6.
Yeah.
And if n were 2, it would be another 12 pi over 6, so it'd be 35 pi over 6. So if I wanted to give you an answer that included everything that I have circled, the way I would refer to it would be 7 pi over 6 plus n 2 pi, or 11 pi over 6 plus n 2 pi.
Okay.
I'm trying to think if there's a simpler way to give that answer. I've always kind of objected to these questions because they kind of confuse without helping. Most of these questions give you a domain restriction. In other words, they would say x is greater than or equal to 0 or less than or equal to 2 pi, putting it in the unit circle, making this and this your answers, where n is 0. When I give an answer that includes the entire domain, well then n are all real numbers, all real integers. So n could be negative 1, could be negative 2, negative 3, negative 4, and could be 0, and could be 1, it could be 2, and could be 3, and could be 4. So notice that giving the answer like that covers all combinations of 7 pi over 6. And giving the answer like this covers all combinations of 11 pi over 6.
Okay.
And that's what you want. In other words, the real answer to the solution of that equation are both of these that I have in rectangles.
Okay.
I'm trying to figure out if I can simplify that at all. Let me think for a second. Let's see. If I said, I don't think so. I don't think I can simplify it. No, I believe. Do you have answers on these?
No, not on these ones, unfortunately.
I would be curious to see what their answer was. But I believe the full answer is in what I have in both rectangles. Certainly.
I think that's true too.
Yeah, that produces answers, and all of these are valid. Every answer here is valid, including the 7 pi and the 11 pi.
Yeah.
Basically, it's not just these two answers, but multiples of 2 pi also. In other words, if I said to you, the sine of x is 30 degrees, excuse me, if I said the sine of 1/2, now, let me start again. If I said the inverse sine of 1/2 equals, well, what does it equal? It equals 30 degrees, but if my domain is not restricted, it's also equal to 150 degrees, and it's also equal to 390, and it's also equal to 410. In other words, if you took the inverse sine, Or if you took the sine of any of these four angles, you get 1/2. And that just keeps going up. In other words, I keep adding 360 to that, and I keep adding 360 to that.
Yeah.
And
Okay.
all of those, so I could put my answer at 30 degrees plus n times 360, or 150 degrees plus n times 360. So
Yeah.
that would cover all possible answers for the inverse sine if you did not restrict the domain. Now, when you put this problem into a calculator, it restricts the domain to first quadrant only for positive arguments and fourth quadrant only for negative arguments. In other words, if I put into a calculator the inverse sine of -1/2, it's going to give me the fourth quadrant answer only, minus 30 degrees.
Okay.
And if I do inverse sine of +1/2, it's going to give me the first quadrant only, 30 degrees. It's not going to give me the second quadrant. And it's not going to give me the second quadrant again. In other words, it chooses one or the other. And the reason is that they're called inverse functions. They have to pass the vertical line test. I can't have the calculator giving me two different answers for the inverse sine of 1/2.
Yeah.
I want one answer only. So it changes it to first quadrant for positives, fourth quadrant for negatives, which is completely arbitrary. Mathematicians could have chosen second quadrant and third quadrant if they wanted, but they chose first and fourth. And that's only for sine and tangent. For cosine, or inverse cosine, I should say, positive arguments produce a first quadrant angle, negative arguments produce a second quadrant angle, not fourth.
Okay. Okay.
So what else we got?
The next one is 5 equals secant squared of x plus 3.
Okay. It's the first thing we want to do. Again, no restriction on the domain?
Yeah, no restriction on the domain.
Well, I'm going to add one. I think it's more educational if you make the answers in the unit circle, and then I'll give you the answer for the entire unrestricted domain.
Okay.
Because you have a lot of questions like this, where your domain is restricted to the unit circle.
Okay.
What's the first step?
Subtract 3 from both sides.
Okay, so now I got this. Now what?
Square root both sides.
Okay, good. What's the left become?
Root 2 over 1.
It's plus or minus root 2.
Oh, plus or minus root 2.
Plus or minus is critical because that gives you two more quadrants as opposed to just plus. There's one rule I try to teach all my students, and that is, if you are solving an equation by taking the square root of both sides, always begin your answer with plus or minus. If I tell you that x squared is equal to 4, then x is not equal to just 2, it's equal to plus or minus 2. Notice that minus 2 squared is plus 4. Plus 2 squared is plus 4. So even with polynomials, it's the case where you always begin your answer with the words plus or minus when you're solving an equation by taking the square root. All right, now we have to figure out where the secant of x is equal to plus square root of 2 and also minus square root of 2. Well, in the unit circle, each of these is going to have two answers, two different quadrants. So this should give us all four quadrants. So what's
Okay.
x? What's one quadrant? In other words, where would the secant of x be equal to plus square root of 2?
Pi over 4.
Good. Man, I love it that you're thinking in radians. That's not easy to do. How about the second quadrant?
3 pi over 4.
Well, that's where it would be equal to minus square root of 2.
Oh,
Because,
okay.
well, that's one of the answers, because it's plus or minus.
Plus or minus, but okay.
Is that all four quadrants are going to give you an answer. Okay.
So the
if it was plus square root of 2 only, then the answer would lie in the first quadrant and the fourth quadrant. In fact, let's make sure we write it that way. What's the fourth? Since secant is reciprocal of cosine and cosine's positive in the fourth, what's the fourth quadrant angle that secant of that angle is equal to plus square root of 2?
7 pi over 4.
Okay. So those two angles in the unit circle, it's equal to plus square root of 2. And 3 pi over 4, it's equal to minus square root of 2. And 5 pi over 4 is equal to minus square root of 2. So this would be your four answers if this were the question.
Okay.
Now, let's take
if it was in between 0 and 2 pi, I get it, yeah.
Yeah, because that's the unit circle. And those are the four quadrants, where the secant of each of these angles is equal to either plus or minus square root of 2. Now, let's take that out so that we can phrase this in a way where the domain is not restricted. In other words, I want all combinations. Well, looks to me, if we try to put this into some sort of a series, how about pi over 4 plus 2n pi over 4. And let's see if that covers every single angle. When n is 0, we get that. When n is 1, doesn't work. Didn't phrase it right. Now, let's see. Got to give two answers. Got to give two answers. One would be if
n2 pi.
Well, yeah, you can always do it that way. Maybe that's the best way to always do it. But then you have to also do the 5 pi over 4 separately plus n2 pi. So that would do it. I was thinking that there had to be a way to do it a little bit more straightforward, and I think there is. In other words, let's go back a moment. We've got.
Wait, I have one question though.
Yeah.
Why would you put the 5 pi over 4 instead of the 7 pi over 4? Because if you just put pi over 4 plus n2 pi, doesn't that... Oh, wait a second.
Let's go back and rearrange our answers. Those were our four quadrant answers, okay? Let's see if we can write this with one series notation. Well, we got x equals pi over 4, which gives us this one. How do we get that one? Well, let's see. If we add n 2n pi over 4, when n is 1, we get this one. When n is... No, we don't get that one. How do we get that one? come I can't figure this out? In an easy way. How do we get this one and this one and this one with one expression? Let's say I want to add. No, that's correct. I was correct. 2n pi over 4. Yeah, now when n is 0, we get this one. When n is 1, we do get that one, 3 pi over 4. When n is 2, we get 5 pi over 4. Do you see that?
Yeah.
When n is 3, we get 7 pi over 4. So here's a case where we don't need two different expressions. That covers it all.
Okay.
In other words, that gives us every possible answer where n's domain is minus infinity to plus infinity.
Okay.
I should say integers from negative infinity to plus infinity. They have to be integers.
Okay.
Now, a lot of times, if you arrange your answers in order, and if you do just the unit circle and arrange your answers in order, you can frequently figure out the pattern and write it as a single arithmetic series. And that's what that is an arithmetic series.
Okay.
All right, what else you got?
Next one is 2 equals 4 cosine squared x plus 1.
Okay, work me through the steps. Did I write it correctly?
Yes.
Okay.
I'm unsure. I mean, you could subtract 1, but I don't think that would really get you anywhere.
Yes, it actually does. Treat all of these trig equations as if they were polynomials. In other words, solve this the same way you would solve this. You subtract 1 from both sides. Then you would divide both sides by 4. Then you would take the square root of both sides. That's how you would solve this polynomial equation. Well, let's solve this trig equation exactly the same way. So the next line is this. Give me the next line.
The next line is 1 over 1/4 equals cosine squared x.
And the next line.
So the square root of 1/4 equals cosine x?
Yeah, what is the square root of 1/4?
1/2?
Uh-huh.
Oh, okay.
Again, it's plus or minus 1/2.
Oh, plus or minus 1/2.
Okay. Now, in the unit circle, let's find out everywhere where that occurs. How about the first quadrant?
Pi over 3?
How about the second quadrant?
2 pi over 3?
This is where it's plus.
Yeah.
That's where it's minus. Next one.
2 pi over 3, 2 pi over 3. 4 pi over 3?
Again, it's minus, third quadrant. And finally?
5 pi over 3.
Fourth quadrant, plus. So that covers the 4 angles in the unit circle where cosine of any of those angles is either plus or minus 1/2. With me?
Yeah.
Now let's figure out if we can write that in one single arithmetic sequence. I don't see us being able to do that because this is 1 pi, 2 pi, 4 pi, 5 pi, Next one's going to be 7 pi over 3. Next one would be 8 pi. Well, maybe we can write it in a single. In other words, that's the same as 2 pi over 3. But then this one becomes 10 pi over 3. So it's a sequence that looks like 1, 2, 4, 5, 7, 8, 10, 11. I'm not sure I know how to write that sequence in terminology, except by saying x equals this one, pi over 3. And then how do I get that one? I have to add
Did you have to add
That's
5?
not the one I want. Yeah, I want this one here. So I want to add n pi, and then that gives us this one, and this one. And the other answer is 2 pi over 3 plus n pi. And that gives us this one, this one, and this one.
But you don't write it as in like pi over 3 plus n pi over 3?
Well, let's see. Pi over 3 plus n pi over 3. When n is 1, I get 2 pi over 3, okay. When n is 2, notice that I get 3 pi over 3, or just pi, and that's not one of the answers.
Okay.
So that doesn't work. In other words, always make sure when you come up with, these are the hardest equations to solve, because you always have to figure out this terminology. The much easier equations are first quadrant, or rather unit circle only. And in unit circle only, those are my 4 answers right there. I don't have to worry about anything else. And I just list them as 4 answers. I don't put it into in-term terminology.
Okay.
But if I'm trying to allow my domain to be all real numbers, in other words, x to go from negative infinity to positive infinity, then I believe that covers all our answers. When n is 0, it gives me the first 2. When n is 1, it gives me 4 pi over 3 and 5 pi over 3. So as long as I get those first 4 answers with both of these, then as n goes up, I'm in the second unit circle and then the third unit circle and so forth. So I think this is the answer, but these are tough. It's tough to take your answers and put them into this terminology. And sometimes you have to do it with 2 different expressions. In other words, x is either equal to pi over 3 plus n pi or 2 pi over 3 plus n pi. And n is all integers from negative infinity to positive infinity, and that does cover all my answers. And I think that's the most simple way of describing all of my answers.
Okay.
The way you can tell whether somebody's taking an honors trig course or a regular trig course is this problem.
No.
In other words, if you have to put your answer in terms of this n terminology here, that's an honors trig course. Or a trig course that's gone a step beyond Common Core. This is not Common Core. Common Core would always be restricted to where you were in the unit circle. And they wouldn't make you go beyond either before or after the unit circle. Only when you get outside the unit circle that you have to start describing stuff in this terminology.
Okay.
Okay? And in a way, I find that a little bit confusing. Like I said, that if I was teaching somebody trig from the start, I would always restrict it to the unit circle to begin with. That would be the beginner slopes. And then maybe the medium or black slopes would be where you don't restrict the domain. You let it go from negative infinity to positive infinity. Then it's a much harder problem. Well, much harder in the sense that you have to figure out how to write your 4 answers in terms of a proper arithmetic sequence. What else you got?
Okay. The next one is 4 tan x minus 7 equals 3 tan x minus 6.
Okay. Treat this just like an algebraic equation. Solve for tan x, and then we can solve for x.
I will subtract 6 from both sides, and that becomes 4 tan.
And add. I tell you what, these become easier if you take care of the trig function first.
Okay. So maybe then I'll subtract 3 tan from each side?
Yeah, that leaves tan x over on this side, which is perfect. Which tells me that I'm going to move this negative 7 to the other side. In other words, by treating the trig function first, it tells you which way to put your which side to put your variables on, which side to put your numbers on.
Okay.
Notice that had I added 6 to both sides, I would have had minus 1 here. I would have had minus tan x there. Then I would have had to deal with those negative signs. You always want to move, when you're solving any algebraic equation, whether it's polynomials or trig functions, you want to stick with positive numbers if you can.
Okay.
Makes everything easier.
Okay.
Okay. So within the unit circle, let's solve that problem first. I'm convinced that's the way to go anyway, regardless of whether your domain is restricted to the unit circle or unrestricted, as your problems are. The best way to proceed is let's solve it in the unit circle. Where between 0 and 2 pi is this true?
Pi over 4 and what's that one? 5 pi over 4.
Well, you're getting good. You're learning your trig, Nick.
Thank you.
Okay. And let's list the next couple. In other words, in the second unit circle.
It would be, oh man.
Add 2 pi to your first number and add 2 pi to your second number. That's the way you do it.
Okay. So it would be 9 pi over 4 and 13 pi over 4.
Okay. Now, that's all the places in the unit circle that satisfy this equation. Now tell me how I can write that as a infinite series.
You could write pi over 4 plus, oh man.
What's the difference between 5 and 9 and 13?
5, 9, 13, 4.
So 4 pi over 4, right? In other words, I get from here to here by adding 4 pi over 4. And then I get to there by adding 4 pi over 4. And then I get to there by adding 4 pi over 4. Well, 4 pi over 4 is pi.
Okay.
So I think that does it. In other words, in one equation, we can answer all the answers here. And now let's just check it. When n is 0, we get this answer. When n is 1, we get that answer. When n is 2, we get that answer. When n is 3, we get that answer, so forth and so on, including negatives. When n is minus 1, we get minus 3 pi over 4, which is the answer. Minus 3 pi over 4 satisfies that equation also.
Okay. Huh.
So I'm going to suggest you do that on every one of these, which is to say, find all the answers in the unit circle, try to write, ideally, a single expression that encompasses all of those answers. And if you frequently, you cannot do a single expression. You got to do two different expressions.
Okay.
So your answers are either going to be one answer or two answers, as we saw in the last problem. We could only express that series with two different answers.
Yeah.
All right, let's do another one.
The next one is 9 plus cotangent squared x equals 12.
Okay, next line.
Cotangent squared x equals 3.
Not 3. What's 12 divided by 9? Oh,
But why?
my mistake. I totally apologize. Next
That's okay.
line.
Cotangent of x equals root 3.
How do you begin your answer every time you're solving an equation?
Plus and minus root 3.
It's huge. Notice that gives us two more quadrants. Okay, where's x? The triangle. There's 1.
Oh man.
Root 3 and 2. That's a 30-60 triangle. Okay, so where is cotangent equal to root 3?
Cotangent equal to root 3 at pi over 6.
Good. Now, where else? Is it plus 3?
What's 7 pi over 6?
Good. So those are the two places in the unit circle where cotangent of either of these angles is equal to plus root 3. Now how about minus root 3? That would be second and fourth quadrant.
5 pi over 6.
Good.
And 11 pi over 6.
And give me the very next in the second quadrant.
Sorry?
If, in other words, this is just the unit circle, before I can figure out how to write this in an arithmetic infinite series, I want to know what the very next one is in the fifth quadrant.
Wouldn't it be 13 pi over 6?
Okay. Now that gives me enough information to go on. Can you write a single expression that expresses that infinite series?
X equals pi over 6 plus...
The answer is no, you can't.
No, you can't.
You have to write it in two expressions. Well, how do I get, in the way these always alternate, how do I get these answers? Those three answers right there in one expression. Pi over 6 plus what?
Plus Oh man. N 5 pi over 6?
N pi.
It's just N pi?
Well, notice that they're each separated by 6 pi over 6.
Oh, okay.
That's pi. In other words, when n is 1, I get this. When n is 2, I get that. Okay?
Okay.
Every other term is going to be these terms here. How do I express those answers?
5 pi over 6 plus N pi.
Now, I might be wrong, but I do not believe there's a way to express both of those in one. As long as I've been working with this, I honestly, I don't get that many opportunities to use N terminology because most people don't use it. But I'm glad every now and then I get a student that uses it because it refreshes me. And as long as I've been tutoring, I can always remember that you can either express these in 2 expressions or 1 expression. And it just depends on the sequence that you're looking at. It's hard to go 1, 5, 7, 11, 13 with 1 expression. But I can go 1, 7, 13 with 1 expression. And then I can go 5, 11, 17 with 1 expression.
Okay.
And between the 2 of them, I get that. So I would suggest doing the following. Figuring out all 4 solutions in the unit circle, which you're good at, and then figure out the 5th quadrant, just so you have another number to look at.
Okay.
And you're looking at the numbers 1, 5, 7, 11, 13. I don't know of a way of expressing that in 1 expression. I'm just not sure you can do it. But the first expression can express that, that, and that. And the second expression can express that, and the next one, which would be 17.
Okay.
Okay. I'm pretty sure that's the way these have to be done. Unless I'm just completely going senile, I'm pretty sure that there are lots of solutions that you have to give in 2 expressions.
Okay.
Okay.
Okay. Okay, the next one is 2 minus 10 secant x equals 4 minus 9 secant x.
Which side should we put our variable and which side should we put our numbers? In other words, whenever you're solving an algebra equation, that's always the first question you have to ask yourself. And am I going to put the x's on the left and the numbers on the right, or am I going to put the x's on the right and the numbers on the left?
I would say the next line is going to be 2 minus secant x equals 4.
That's going to leave a negative sign in front of the secant x.
Okay, so
think about it is if I move this to the right, it's going to leave me with a positive sign in front of the secant, correct?
Yeah.
A subtle point, but nonetheless, that's what I use to determine which side I move my variables on. It's whatever gives you a positive sign in front of the variable, which means I'm going to add 10 secant x to both sides, which gives me 1 secant x over here. And then I'm going to move this 4 to the left, which gives me minus 2 there. So I still have a negative sign, and that's unavoidable. The other option would be negative secant x equals positive 2. which is the same thing, but just a rule of thumb, when you're trying to answer that decision as to which side to move your variables to, always move your variables to the side that leaves you with a positive coefficient in front of the variable. It's just an easier starting spot. And there will be times where that will give you positive coefficients in front of both sides. Okay? Now, in the unit circle, where is this true? Nick, you still there?
Yeah. Sorry, I was just looking at it.
The way I do these, I don't know how you do them. Maybe you've incorporated all 6 trig functions into your brain. Me, these secondary ones, I always have to convert to the primary ones. I know that secant is the reciprocal of cosine. So I'm really looking at where the cosine would be equal to minus 1/2.
Yeah, I get stuck up on these ones where it's like secant.
Well, that's why I put them in there, is because you're in the hard class. But notice that this is the same exact problem as minus 1/2 equals cosine of x. Those two are the same.
Oh.
In other words, if cosine x equals minus 1/2, then secant of x has to equal minus 2, right?
Mm-hmm.
One is the reciprocal of the other. So if it makes you think about it any clearer, that's not a bad next step to take.
Okay.
Now, where's x? Where's the cosine of x equal negative 1/2?
It's 5 pi over 6? No, no.
What quadrants are cosine negative in?
The second and third.
Okay, so let's have a second quadrant angle.
Uh,
What's the second quadrant angle that's the equivalent of pi over 3? Because if we were talking, about cosine x being equal to 1/2, that would be pi over 3, right?
Mm.
So I want the second quadrant angle that's the equivalent of pi over 3.
And that's 2 pi over 3.
All right, that's the second quadrant.
And the third quadrant is 4 pi over 3.
Okay. And let's do the fifth quadrant. Let's see whether we can put it into a sequence with one line, or do we need 2?
The fifth quadrant is 7 pi over 3?
Let's see. If I take that and add 2 pi to it, I think that gives me 8 pi over 3.
Oh, 8 pi over 3.
And if I take this one and add 2 pi to it, I get 10 pi over 3. So now my sequence is 2, 4, 8, 10. Or I should say 2/3, 4/3, 8/3, 10/3. Again, I don't believe I can do that with one sequence. In other words, some of these you can do with one sequence, some require 2 lines. So I'm going to tell you this is a 2-liner. What's the first one? And the way you get the first one is you take that, every other one.
Isn't it 2 pi over 3 plus n 2 pi?
You got it. And what's the second one?
4 pi over 3 plus n 2 pi.
Yeah. But that's the way these always turn out to be. In other words, to find the first line of your series, take every other one. And to find the second line of your series, take every other one also.
Okay.
Okay? But
the next another one of those.
The easiest first step is to find all four answers in the unit circle, first of all. Maybe an answer in the fifth quadrant as well. Here we did, let's see, this was second and third. This was actually the sixth and seventh quadrants. But it wasn't until we listed the answer for the sixth and seventh that we could tell we had a series that couldn't be represented in one line. In other words, if I was looking at first quadrant only, then it looks like I might be able to show that as 2 pi over 3 plus n pi over 3, or 2 pi n over 3. But that's an illusion that I get by just looking at the first or the unit circle only. If I go out at least one more unit circle, you know what I mean by that?
Yeah.
If I go out 2 unit circles, then I'm for sure going to see a sequence that'll let me know whether I have to write it in one line or 2.
Okay.
All right. Got time for one more.
Yeah. The next one is 3 cosecant x equals 2 cosecant x plus root 2.
Okay, next line.
2 or cosecant x equals root 2.
And unit circle answers. And, well, I tell you what, let's add a different step. Since you appear to be the same way as me, write this in terms of sines and cosines.
Sine x equals 1 over root 2.
There you go. Now, to me, this is easier to solve than the line above it. Do you agree?
Yeah, I do. Yeah.
And I think that teachers would agree also. So doing this step actually does simplify the problem a little bit. You don't have to do it if you can think of it in your head. But now, in the unit circle, what are my answers?
Is it pi over 4?
First quadrant.
First quadrant, and then I need the second quadrant, and it's 3 pi over 4?
And the fifth quadrant.
Fifth quadrant is 5, no. Is it 5 pi over 4?
No, excuse me. That was my mistake.
No, does it become 9 pi over 4?
Yeah, I got to add 2 pi to that first number.
Yeah, that's what I messed up on too.
It's 9 pi over 4. And then add 2 pi to the second number, and you get 11 pi over 4. So now our sequence is 1, 3, 9, 11.
Okay.
In other words, that pretty much tells you you're going to need 2 lines, right?
Yeah.
If I had a sequence 1, 3, 5, 7, 9, like we did on one of the problems, well then I have to find that sequence in one line. It's just the first thing plus 2 times n.
Yeah. Okay.
But when my sequence is 1, 3, 9, 11, then I kind of have to go every other one. I got to do that. I got to do this one and that one. Remember, these are over 4. So what's my first answer going to be?
It is going to be pi over 4 plus n2 pi.
Yeah, and that's pretty common. In other words, whenever you need 2 lines to do it, the second part's almost always 2n pi. And what's the second part?
3 pi over 4 plus n2 pi.
Yeah. Now, it shocked me horribly if somebody came up with a way of expressing that in one line. And if your teacher has a way, please let me know so I stop tutoring it this way. But
Okay.
I'm pretty sure that when you have these kind of sequences, you have to do it in 2 lines. Yeah, by all means, if your teacher does come up with a way of expressing this sequence in one statement using n terminology, I don't know how you would do it, because as n goes from, when n is 0, you always get this answer. And then when n is 1, you got to get that answer. So I would have to add 2 pi over 4 times n, which would be pi over 2, and then when n is 3 or 2, you don't get that answer. So I don't see any way of doing it with one expression. I think you got to use 2.
Yeah, I think so too. I don't see any other way that you could do it with one expression. I only have the trouble with when it gets to like the reciprocals of the sine, cosine, tangent.
This should solve all of those problems.
Yeah, we're adding that extra step. I think that definitely makes it a lot easier.
I have never done that before, to be honest with you, but I see now that it actually is quite helpful, because I'm not the only one that thinks in terms of sine, cosine, and tangent. Most people do. If you were to ask most people, are there 3 primary trig functions, they would say yes, and then they would say the other 3 are secondary trig functions. Even though that's not really true, all 6 are as important as any of them. But it's probably because the older calculators, the TI-84, only had sine, cosine, and tangent keys. If you wanted...
Do the newer ones have like the reciprocal?
Yeah, the TI Inspire does. In other words, if you go into the TI Inspire and hit the trig key, it gives you all 6 trig functions and at the same time all 6 inverse trig functions. So you can actually work with cosecant in the Inspire. You can't in the TI-84. Which do you have?
I have the TI-84 Silver Edition Plus, I think.
Yeah. So you're only going to have sine, cosine, and tangent keys. And if you want these reciprocal functions, you have to actually take the reciprocal to figure it out. In other words, if somebody says, what's the cosecant of 30 degrees? Well, you wouldn't be able to do that directly on your TI-84.
No.
You would have to find the sine of 30 degrees and then take the reciprocal of that.
Yeah. Okay, I see how that works.
That'd be the only way to do it.
Yep.
Nick?
Cool.
Have a good week, and I will talk to you next time.
I will talk to you next time. Thank you, Mr. Cohen.
You're welcome.